In this tutorial we are going to design and simulate two elements array of an inset feed microstrip patch antenna which is operating at 2.45 gigahertz using CST. So we will use the previous design of simple microstrip patch antenna, and that antenna was operating at 2.45 gigahertz. Alright, so these are the results of its S parameter, and it was going to provide us the gain of 6.02 dBi. So we will use this simple microstrip patch antenna, and then we will construct its two element array. So if you want to know about the basic design steps of this simple microstrip patch antenna, then we have already designed it in tutorial number 9, and the link of that tutorial has been provided in the description as well. So as far as its design of array is concerned, basically antenna arrays can be constructed using different methods like series feed, like corporate array, tapered line, and lambda by 4 are quarter wave transformers. So there are a lot of methods in which we can design antenna array. So these are the different figures. So part A is about the tapered line. So the basic problem while designing antenna arrays is its impedance matching. So in tapered line, if we want to design 4 elements array or 2 elements array, then all the feed lines must have 100 ohms impedance, right? Similarly, if we have to construct the array, or we have to design an array using a simple quarter wave transformer, which is the most important and most common method of designing an array. So in that method, our first feed line, which is directly attached to the patch, must be 100 ohms, and then 50, 70 and 100 ohms feed line, and then the last one must be with the 50 ohms impedance. Okay, so these are the different values of the impedance of different feed lines in this lambda by 4 or quarter wave transformer method. But it has been more simplified that you can, instead of designing these 3 steps with 50 ohms, 70 ohms and then 100 ohms, you can use a single line here with the impedance of 70.71, right? So that will be the equivalence impedance of this middle feed line. So how you can calculate its equivalent impedance? There is a very simple formula here. So if you have to calculate the equivalent impedance, so that equivalent impedance, or Z0, will be equivalent to the square root value of the Z1 multiplied by Z2. So as you know that its Z1 is 50 ohms and Z2 is 100 ohms, so that's why 100 multiplied by 50 will be 5000, and if you take its square root, then it will be equivalent to the 70.71 ohms. So simple quarter wave transformer method can be simplified that the width of this feed line will be considered as a 70.71, right? While the impedance of these top feed lines will be 100 ohms, and the last feed line, which will be attached to the waveguide port, will be 50 ohms. So in this way you can use simple quarter wave transformer to construct 2 elements or 4 elements array, right? So now let's move towards its design in CST. So first of all, this is our single microstrip patch antenna. So now you can just copy this simple patch from transform option, and then just copy it, and now you have to just copy it at some distance from this patch. So as far as the distance between these 2 patches is concerned, so you can use the distance of lambda by 2 or lambda by 4 between these 2 patches, right? So I am just talking about the distance between the edges of these two patches, not between the origin of these two patches, right? So for example, if we are going to use the distance of lambda by 2 between these two patches, and you know that the value for its lambda as per the calculations that we have already used in our previous tutorial as well. So its lambda by 4 is 14.58 and lambda by 2 will be the product of 14.58 multiplied by 14.58. So the total distance between these 2 points must be the product of 2 and 14.58, right? So that will be the distance between the center of these two patches. And as you know that this is basically the width of this patch, and half of the width will be considered to move toward the one edge, and half of the width will be considered to move toward another edge from the second patch. So that's why we have to just add its width as well, and its width is around about 37. So you can use simple plus w, right? So that will be the proper distance between these two patches, right? So you have to for example, if you have to move it along the x-axis, then you will put these values in the translation vector of x, right? So that will be the proper distance between these two patches if we want to use the distance between these two patches as a lambda by 2, right? So now just click on OK. Okay, so now you have to add the further feed lines, and you have to change the feed lines of these patches as well, because this feed line is represented with the variable wf, and wf is 3.08, and 3.08 means that its impedance will be 50 ohms, right? So calculation method have been already discussed in previous tutorial as well. So for 3.08 mm its impedance will be 50 ohms, right? But now in this design you have to just provide the 100 ohms to the feed line that is directly attached with this patch, right? So for 100 ohms its width must be 0.7 mm, or this is represented with the variable of wf3, right? So first of all it would be better if you add more variables, right? So wf3 and wf3 will be equivalent to 0.7, right? So its value will be 0.7, and similarly wf2 is for 70.71 ohms, right? And its thickness is 1.64, right? So it will be 1.64. So first of all for the proper impedance calculations you have to little bit change in this patch, and as you know that this brick is basically the width of feed line, so that's why instead of using wf you should use wf3, right? Because wf3 is equivalent to the width of 0.7, right? And 0.7 is basically providing us the impedance of 100 ohms, right? So that will be wf3. Now you have to construct another feed line which will be constructed between these two patches, and you know that as per the quarter wave transformer, and its equivalent impedance must be 70.71, and 70.71 means that we have to use wf2 and its value is 1.64, right? So just go to the modeling, and now you have to just name it as a feed line 2, right? So it will be feed line 2, right? So now we have to just put the value of x min and x max here. As you know that in our last video we have constructed this simple microstrip patch antenna at the origin, right? So yeah, this is its origin along x-axis, right? So as you know that this is the basically origin of this patch, and we have to start little bit from the left side of this origin. So that's why the total width of this feed line was WF3, and if we take its half along the negative x-axis, then it will be directly touching the left side of this feed line. So we have to start feed line 2 from here, right? So that will be its starting point, right? So from starting from here further, we have to add the distance, and distance is represented with 2 multiplied by 14.58, and we have further added the width of the feed line, right? So if we use that distance, now we will be touching the this point of the feed line, right? So just click on preview, but before clicking on preview you have to adjust the values of y min and y max as well. So what about the value of y min and y max? As you know that previous antenna was designed at the origin, so along y axis if we move downward, then that was the basically minus L by 2, because along the y axis its length was L, and half of its length was at the bottom side of this patch, so it will be minus L by 2, and further we have to move toward the length of feed line, and its length of feed line is represented with LF, right? So its starting point will be minus L by 2 minus LF, and further we have to move toward the bottom side, and we have to define the width of that feed line. So now the width of that feed line must provide a 70.71 impedance, and for that purpose we have defined the variable WF2. So now we will further add WF2 here, right? And as you know that its position along z-axis is 0.035 plus 1.6, and you have to further add 0.035 in its Z max, right? So same material will be used, and now you have to just click on preview. So now you have to focus on the starting and ending point of this feed line. So its start point is accurately defined, right? So now just check its this ending point. So it is just touching the start point of the feed line, and its total width is WF3. So if we just add WF3 in Z max, then it will automatically touch the end point of this feed line, right? So now all the dimensions for this feed line are correctly defined. So just click on OK, and you have defined the second feed line between these two patches. So the last step in this patch area is that you have to define another feed line, and that will be the final feed line, right? So you can name it as a feed line 3. So as far as its central point is concerned, now you have to define this feed line at the center of this feed line, right? So now you have to take some reference points, and you know that the reference point along this feed line is basically minus WF by 3, right? So F3 by 2, right? And now further we have to add the dimension of total distance, and total distance is 2 multiplied by 14.58 plus W, which is the width, right? So that will be our reference point. So that will be the reference point, which is basically in the center of this feed line, right? But as you have to define the center, so that is the total distance starting from this and this. But if we have to calculate the average distance, so obviously we will have to take the average between these 2 points, right? Starting point and the ending point, right? So that is basically the starting point, which is WF, and the total distance is this. So in total distance we have to just add half of its distance, right? So that's why we will just take its half, right? So half of the total distance plus its starting point, right? So that will be the central point while defining the x min and x max points, but that is the reference point. So now the total width along the x-axis of the newly defined feed line, which is named at feed line 3, is basically represented with WF. So if we have to define it at the center, so its half will be along the x min point, right? And its half will be lies along x max point, so it will be WF by 2, right? So these are the different values of x min and x max for the newly defined feed line. Now we have to define the reference points. So reference points along the y axis is very simple, because y max will be minus L by 2 minus LF minus WF2, because that point is basically minus L by 2, and from this point to this point there is a value of LF, and then there is a width of this feed line along the y axis, and that is WF2. So that will be our starting point, and we have further add length of feed line to this point, right, along the y min. So as you know that its values along z min and z max are 0.035 plus 1.6, and z max will be 0.035 plus 1.6 plus 0.035. Same material will be used. Just click on preview, and now you can check that we have properly defined the feed line, and its position along the x-axis is accurate, because it is exactly in the middle of this feed line, and its starting and ending point is accurate as per the demands or requirements, right? So that is the procedure of defining proper two elements and just constructing different feed lines as per the quarter wave principle. So now in next step we have to basically increase the size of ground and substrate, and then we will simulate this array. So for defining the end point of the ground and substrate along the y min or the negative y axis, so we can just copy the value of y min from here, right? So just copy the value of y min from this point, because we have to touch the bottom of the ground and substrate with this point, right? So that's why instead of again defining the value of all variables, so I am going to just copy these values, and we will directly paste these values while increasing the ground and substrate along y axis, right? So just go to the substrate, and now you have to put the copied value in y min, and you will observe that it is directly touching the end point of this feed line, right? And similarly we have to increase the size of substrate along the x max as well. So as you know that along the x max we have simply added another value of the separation or the value of the distance between these two patches, and that value can be taken as 2 multiplied by 14.58 plus w, right? So just click on preview, and you can observe that the substrate y min y max and the substrate y x min and x max values are properly defined as per the demands, right? So just click on OK. So in a similar way you have to increase the values of ground as well. So you have to paste the value of y min and you have to add the value of distance in x max as well, right? Okay, so that is the simple procedure of constructing simple array, and now you have to add all these patches and all the feed lines, right? So just select all these things and just add them, right? So that is a simple way of defining or constructing two elements array by using a quarter wave transformer method. Now you have to simply define the port, and you have to basically delete the previous port as well, and you have to define a new port at its accurate position, right? So just zoom it in and you have to select its face. So you can use the simple shortcut key by pressing F, and you can select this surface, and now you will go to the modeling and you have to define the waveguide port. And as you know that along the x-axis its width must be the 2 times the width of feed line, right? That we have already discussed in our previous videos as well. And now Z max, in Z max you are at the top position and you have to touch the ground as well. So simply you can use the value of 1.635, because your ground is going to start from 0, so the overall value will be taken as 0, so your feed line will touches the ground as well. And as far as the value of Z max is concerned, it must be the 4 times the height of substrate, right? So just click on preview and you can just press OK. So that's all about the design of a simple 2 elements array using lambda by 4 transformer method, right? So as far as the field monitor is concerned, you have already defined the field monitor values as well. You need just its gain and S parameters, right? So now you can start the simulation, right? So after a successful simulation we will discuss about its results as well. So simulations will take some time, so after completion of simulation we will check its results. So simulations have been completed, so now let's check the results of this 2 elements antenna array. First of all, if I discuss about the S parameters, then it provides almost minus 34.046 at 2.44 or around about 2.45. so its S parameters have been properly improved after designing its 2 elements array. Similarly we can check the results of gain as well. So now it's going to provide the gain of 8.82 dBi with its 2 elements array. So that was the basic purpose of designing array to improve the gain. So that's all about the design and simulation of 2 elements array. In our next video we are going to discuss about the design and simulation of 4 elements array. So please subscribe our channel and press the bell icon so that you can receive the notifications of our latest videos. Thank you.